Imagine floating alone in space. Ahead of you, a black sphere darker than night itself, a black hole. There's no light, no reflection, just absolute void. Now imagine moving closer. What happens next isn't just bizarre, it's scientifically terrifying. Would time slow down? Would you be crushed? Would you live for a few seconds more? Today, we dive into real physics, not science fiction, to explore what would truly happen if you fell into a black hole. From warp time to spaghettification, this journey may bend your mind more than gravity bends light. So, what is a black hole really? At its core, a black hole is the ultimate gravitational monster. It's a region of space where gravity is so intense, nothing, not even light, can escape its pull. They often form when massive stars, at least 20 times the mass of our sun, run out of nuclear fuel. Without that outward pressure from fusion, gravity wins. The star collapses in on itself, compressing into a single, infinitely dense point known as a singularity. This singularity is surrounded by a boundary called the event horizon, the point of no return. Once something crosses this line, it's gone forever from the observable universe. There are several types of black holes. Stellar mass black holes, up to dozens of solar masses. Intermediate black holes, potentially thousands of solar masses. Supermassive black holes, with millions or even billions of times the sun's mass, usually at the center of galaxies. And possibly primordial black holes form in the early universe, though we've never observed one. Black holes are not empty. They are incredibly compact objects with gravity so extreme that they reshape the very fabric of space-time. Now let's say you're approaching a black hole. What do you see? From a distance, it's eerily beautiful, surrounded by a glowing disk of gas and dust called an accretion disk. This material swirls at near-light speeds, heating up and glowing brightly in X-rays. But the black hole itself? Perfect blackness. No light escapes. No image forms. As you get closer, you begin to see light distorted in strange ways. The background stars stretch and swirl, bending into arcs, a phenomenon called gravitational lensing. The black hole warps space around it like a bowling ball on a rubber sheet. Now imagine looking back toward Earth. As you fall, time appears to slow down for you. But even stranger, someone watching from afar would see your descent slow to a crawl. You'd appear frozen at the event horizon, your image redshifted, fading slowly into blackness. But for you, from your perspective, you're falling normally. The moment you cross the event horizon, you won't feel it. No sensation marks the boundary, but your fate is sealed. The event horizon is more than a boundary. It's a trapdoor in space-time. Outside the horizon, you can still escape with enough speed, in theory. Inside, all paths point inward. It's like being stuck at the bottom of a waterfall, the current too strong to swim against. Even light, the fastest thing in the universe, can't climb out. That's why it's black. And here's where physics gets strange. Inside the event horizon, the very structure of time and space flips. Time becomes a direction in space. Falling forward toward the singularity becomes as inevitable as moving forward in time. You can't stop yourself, just as you can't stop time from passing. Now we get to the infamous and real concept of spaghettification. The name might sound ridiculous, but the physics is horrifying. The black hole's gravity isn't just strong, it's uneven. This difference in gravitational pull across your body is called tidal force. In a stellar mass black hole, if you fall feet first, gravity pulls more strongly on your feet than your head. As you fall, that difference grows rapidly. Your body is stretched vertically and compressed sideways. You become thinner, longer, like spaghetti. Eventually, this tidal force overcomes the atomic bonds holding your body together. You are torn apart, first at the molecular level, then atomic, then subatomic. The process is quick, violent, and unavoidable. In smaller black holes, it happens before you even cross the event horizon. But if you're falling into a supermassive black hole, like the one at the center of the Milky Way, the story is different. The event horizon is so large, and the curvature so gentle, that tidal forces at the horizon are weak. You could fall through it and remain completely unharmed for a little while. You would float in silent darkness, drifting toward the singularity. What happens next? As you continue toward the center, tidal forces increase again. Eventually, even in a supermassive black hole, they become deadly. But just before that, something remarkable happens. physics itself begins to fall apart. At the singularity, the center, our equations stop working. General relativity predicts infinite density, infinite curvature of space-time. But infinity isn't a number, it's a sign that the theory has reached its limits. We don't know what's really at the center. Is it truly a point? Could it be a wormhole? Bridge to another universe? Or just the breakdown of reality? This is where quantum gravity, the unification of quantum mechanics and relativity, is desperately needed. But until we have that theory, the singularity remains a mystery. Here's where things get even more complicated and more controversial. If you fall into a black hole, are you truly gone forever? Classical physics says yes, but quantum mechanics says information can't be destroyed. This creates the famous black hole information paradox. Stephen Hawking once proposed that black holes slowly evaporate over time through Hawking radiation, a quantum process where particles escape just outside the event horizon. But where does your information go? Some theories say it's encoded in the radiation that leaks out. Others say it's stored on the event horizon itself, like a hologram. This is the basis of the holographic principle. Or maybe information is lost, and physics as we know it must be rewritten. To this day, no one knows for sure. It's one of the greatest unsolved problems in science. But let's take it one step further. What if falling into a black hole didn't mean destruction, but a transition? Some physicists have proposed radical possibilities beyond the singularity. One such idea is the Einstein-Rosen bridge, or more popularly, a wormhole. In theory, a black hole could be connected to another region of space-time, maybe even another universe through a shortcut. You fall into one side and emerge elsewhere. But there's a catch: wormholes are extremely unstable. Theoretical models suggest they collapse instantly, unless held open by exotic matter with negative energy density, something we've never observed. Another hypothesis? White holes, the mathematical time reverse of black holes. Where black holes only pull matter in, white holes would only eject it. No one's seen a white hole in the real universe, but the math suggests they're possible. And then there's the idea that the singularity doesn't destroy you, it stores you. Inside the black hole's horizon, all the information about your existence might be preserved in a quantum state until the black hole eventually evaporates. In fact, black holes might be the ultimate cosmic hard drives, storing every particle, every thought, every atom you ever were, in ways we don't yet understand. Some even speculate that black holes could be seeds of new universes, that every time a black hole forms, it gives birth to a new Big Bang on the other side of the singularity. A multiverse spawned by the collapse of stars. These are not proven facts yet, but they're not fantasy either. They are ideas emerging at the edge of our best physics. And the truth is, we're just beginning to understand what black holes truly are. Falling into a black hole is more than a thought experiment. It's a doorway to the unknown, a test of our physics, a glimpse into a realm where time, space, and matter obey rules we barely comprehend. And maybe, just maybe, by understanding black holes, we're not learning how things end, but how everything begins.